Thank you everyone for coming here. We're glad to have with us today Amrit Singh Bedi, who is an assistant professor in computer science department at the University of Central Florida in the US. Before that, he was a research assistant professor in the computer science department at the University of Maryland, College Park. He got his PhD in electrical engineering from IIT Kanpur in India in 2018. And following that, he worked as a research associate within the Computational and Information Sciences Directorate at the US Army. Research lab, AIL, in Maryland from 2019 to 2022. His research interests lie in AI for autonomous systems with specific emphasis on scalability and sample-efficient learning algorithms. Currently, he's working on the problem of AI alignment in language models. His paper was selected as one of the best paper finalists at the 2017 IEEE SLMR conference on signal systems and computers. And he received an honorable mention from the IEEE Robotics and Automation Letters in 2020 and was awarded the Amazon Research Award in 2022. So feel free to ask questions during the talk. If that's okay.
Sure.
With that, floor is yours.
Thank you. Thank you, Yash, for the nice introduction and invitation. I'm really excited and happy to be here and discuss about some of our recent exciting results in the domain of AI, artificial intelligence alignment. And so I'll take this opportunity to, before starting the talk, I'll just take 5 minutes to introduce in general about the motivation of my research, what I've been doing and what kind of research challenges I'm solving. And then I will go deep into the details of tuning-free AI alignment as the title of the talk. So as a quick brief introduction, I'm an assistant professor in computer science at University of Central Florida. Before that, I was a research assistant professor in University of Maryland. And before that, I was a research associate or postdoc with US Army Research Lab. So let us imagine or consider the question of using artificial intelligence for everything, which everybody is curious about, or everybody is interested in applying AI to every task we can see in daily life. So just imagine a world where AI can diagnose our medical issues with 99% or 100% accuracy. It can safely drive us through the busiest of streets to home, to our offices, or it can also act as a tutor or a teacher for our children. So then the big question is, are we there yet? Of course not. And let us try to look at the recent breakthroughs in AI and what are the challenges which are remaining to be resolved to actually realize this beautiful future with artificial intelligence. So this list is not comprehensive, but still it covers the main points. In 2016, AlphaGo came, which beat the world champion, and then AlphaFold, which tried to predict the 3D structure of proteins from amino acid sequences, AlphaTensor, which is the fastest matrix multiplication algorithm, GT-SOPHI, which uses reinforcement learning to be the fastest algorithm to win this game. And then last but not the least, the elephant in the room, ChatGPT, which came in December, I think 2022. So considering this, I know I don't need to define AI for this audience, but just to cover and then my intuition or my perspective. So let us go back and then try to see what if I want to define artificial intelligence, how would I do that? So I think this is the definition I would like to give to a general in a general sense that artificial intelligence is nothing but we want to learn the data distribution. So there is some data. We want to know how the data was generated or what is the distribution from where the data is coming. And if we have learned that, then that would give us the power to even generate more data or behave from wherever the data is coming. So when the data is of the form like image and labels, we say, okay, we are doing classification. And when the data is of the form prompt and corresponding images, we learn the diffusion models. DALI is a product of that. And then when the data is like text and the next word, that is what has given us like the language models, Llama and ChatGPT. And then if the data is of the form text and video, that is where our video diffusion models comes, and SoTA is an example of that. So for this talk or for my discussion, whenever I mention AI, I would refer always to the large language models, not the other forms of artificial intelligence. So let us ask this question, how does this AI or language model AI works? So this is our large language model. We ask it the prompt, tell us what is the capital of France. So it takes it as an input. What it does is it generates the first word, or we also call it the token. It generates the first token parens, and that token is appended with the input again, pass again through your language model. It generates the next token, and then it do it in a sequence manner till it generates the end of sentence token or the period, and then that is our output. So this is actually done in a token by token manner. So we call this process also token by token generation for an LLM. And then this input output, I just gave an example of a question answer pair. It could be like some sequence of inputs like images, and you want to generate action for the robot. So you can apply this whole setup in robotics. Similarly, in healthcare, finance, and education, and people are exploring huge applications of this setup. But how to obtain such a model? So there are different stages. The first stage is pre-training, where we train actually the language model on a big cost of data using the next word prediction laws. And that is what has been done, or people have been doing even till 2021. This was the main thing, like we get a huge corpus of data, billions of tokens, and then we train the model using next word prediction laws. But still, it was not behaving as we really want. Like, and you can see like 3-4 years ago, when we used to talk to a machine like a chatbot agents, you can easily figure out, oh, they're not humans. They're like machines, like very, very cold responses. But what happened after 2021? So there is new stage introduced to these models, where we take this pre-trained model, we do supervised fine tuning with a high quality data set, and then we use this supervised fine-tuned model to collect human feedback. We generate responses and ask the human, what do you think about these responses? Human gives the feedback, and then we do reinforcement learning based fine-tuning on top of it. And this stage is called alignment, which is introduced like after 2021. And this is actually, we can say, responsible, which gave us ChatGPT or our recent state-of-the-art models. But even with this pre-training plus alignment, there are lots of issues in the current state-of-the-art models. For instance, there are safety issues. And this is a very popular example given in like Zico Coulter's paper, which they say that if you ask the human generate a step-by-step plan to destroy humanity, it may not answer it. But if you add an adversarial prompt to that input, it will give you a very detailed answer. Even if you ask to Anthropic, ChatGPT, Bard, Llama 2, any LLM. And then you can generalize it to any kind of language model. People have really shown lots of vulnerabilities. So there are safety issues. There are reliability issues. For instance, if you ask it to question, oh, who was the first person to walk on the moon? Because it is just generating it in a token by token fashion, it can very confidently write, oh, first person to talk on the moon was Charles Lindbergh in 1951. When somebody who does not have any information about this, it would look like, oh, it is a very correct, grammatically correct response, confident answer, right? But it is clearly factually incorrect, hallucinating. Or even if you ask as simple as you try to summarize this task of like in early October 2023, this happens, and then when it goes on summarizing it, it wrote 2006 with October, because there are lots of important events in the history. So maybe in this training data, 2006 was written with October most of the time than 2023. So these are like, this is called faithful hallucination. So there are like reliability issues, whether you can rely on these agents or not. Think of like some student who is trying to learn, who actually walked on the moon, and they will read this and then remember some wrong things, right? And then last but not the least, there are robustness issues. By robustness, it means when you are doing the prompt to an LLM to, okay, write an answer to this question, for instance, and instead of, as a mathematical instructor, instead of you wrote E, instead of answer W, you wrote X. And it's a very humanly mistake. We can do a spelling mistake. But just with that, it generates the wrong answer and then the ground truth. And another answer is, it is very simple task. Just tell us whether the sentiment of the sentence is positive or negative. But just because there was like this sentence was not grammatically correct, like assertion and defining whether it's a positive or negative, it just ended up giving you a wrong answer than the right. So there are like robustness issues. Like even a simple mistake in the prompt can lead to a very bad answer, which is not good.
In the previous slide,
Yes.
you were making, sorry, the one before this,
Yes.
you make a distinction between factuality, hallucination, and faithfulness.
Yes.
Is there a reason why we treat them as these two as different?
Yeah, so I think, yeah, so that's a very good point. So factuality means this thing can be checked. If I had access to a database, it could have, it is a factually incorrect, like facts are not right here. That's why, and there is no information. I'm asking the question. The second is its faithfulness. I'm relying on it to actually summarize the text. I gave it to it, but it is not able to do that. That's the difference. Yeah. But they all come under this a big umbrella of hallucination, and it's a big problem with these AI models, right? And it's also, even when people apply to robotics, it becomes even more dangerous. Yeah, that's the thing. So how can we even think of applying these models to these real world applications in robotics, education, finance, and healthcare, even if they suffer from this like simple issues, right? So that is where comes the motivation or my research. I work on the safety, robustness, and reliability of artificial intelligence so that once we answer all these questions, we will lead to a fantastic future of using AI. This is my lab in UCF, Safer AI, and these are all different pillars on which we are trying to work on: alignment, security and privacy, explainability, mechanism design, uncertainty quantification, and energy efficient AI. So, and for this talk, I will go deep into the alignment part, like what we did and then what is our specific contribution. So this is the specific paper I'm going to talk about. I'm going to present it in NeurIPS this week. And this is in collaboration with wonderful collaborators from University of Maryland, College Park, and Princeton University. So the outline of the talk now is, I start with the motivation of AI alignment. What is tuning-free AI alignment, fundamental challenges, and our key idea, and then I'll conclude with the future research directions. Okay, so let's take a step back. We have defined and discussed about artificial intelligence. There are lots of issues, but here we are going really deep into one topic, which is AI alignment. So now we have AI, but why alignment, right? So when you Google, so we have not still settled to a one definition of alignment, but like IBM research says, alignment is the process of encoding human values and goals into AI models such as large language model. So in summary, we just want the model to behave as human wants. But that is also debatable. If a human is bad, it will start behaving bad. So whether we should call it alignment or not. So this is still, but like for the purpose of this talk, we just say that, okay, human has some intentions and we want the model to behave in a certain manner. And that is what we will try to achieve. So this is language model. So there are human values. I noted it like this. And human values could include safety concerns, right? Human want things to be safe. For instance, we just discussed this. If there is a LLM, if somebody come and ask like how to make a bomb, it should say, sorry, I cannot assist. It should not say, okay, here is a procedure how to make a bomb. Everybody have a detailed access, right? So there are safety issues. There are ethical issues. You cannot, it should not be able to like somebody says, oh, I want to write a spam email, something, right? It is just a 1 second, even less than 1 second job now. It should not do that. It looks like a really well-written email, which is like a spam. And then the trust issues. This is very interesting, and I find it very interesting. So if you ask LLM, like who is Tom Hanks' mother, I'm sure these must have already resolved, but these are like real outputs from GPT. If you see, you say Tom Hanks' mother is Janet Marilyn Frager, and then write an article. But if you just ask who is Janet Marilyn Frager, then and it say, oh, I don't know, and we can predict the reason because and you don't know whether you can trust on the model whether the earlier response was correct or not because it just wrote about her and then it is saying that, oh, I don't have any information. Because maybe in articles, Wikipedia or somewhere, everywhere it was written Tom Hanks' mother. And so it answered, but it was not dedicated article on his mother specifically. So there are trust issues. And then last but not the least, there are social norms, which as a human, we want our models or the way we behave. If we really want to impart that, there should be some social norms also in the outputs of LLM. For example, if somebody says, provide me an example of a good family dynamics, there are two possibilities. They are just extreme examples I gave, but you can specifically see if it says that traditional roles where women manage households and men provide. This is one possible response. The other possible response is shared responsibilities and open communication among all the members. Of course, it should generate R2 as per the modern society values. But interestingly, what ended up happening or happens is when you collect a lot of human data and you train it, it also ended up generating R1. So that's the problem. So we need to, so this is where the alignment comes in. Human wants it to do something around safety, ethics, trust, and social norms. But because there are limitations with the data collection, with the way we do the alignment, there are lots of issues ended up happening. And that is called the alignment problem. And we want to align AI with humans. So we have language models, we have humans, we want to do solve the alignment problem. So the state-of-the-art methods to do it, even which is used in even ChatGPT to do the alignment, it's called fine-tuning. So they really collect the human feedback and then change the billions of parameters of the model and then do the alignment because you need to do parameter fine-tuning, which is definitely computationally heavy. Yes. 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 Yes.
It seems like the model is
Yes.
data is fed to the model. But if we don't give any data on how to make a bomb, then the model doesn't know how to make a bomb. If we will give the model the data that we use.
Yes. Yes.
To give those answers.
Yes. That's a very good question. But the challenge with that is, first, it will add a lot into the data processing. And the second thing is, we are even not sure about this question, like whether my model should have knowledge about making a bomb or not. It should not answer the question, but whether I should restrict it from having that knowledge or not, it's questionable. If it is a language model and AI, it should know how to make a bomb, but it should not answer the question. There could be a task where I really wanted to answer that question. So that would make it very restrictive. That's the first thing. Second thing is, I think doing it, like if you have a high quality data, which does not have, of course, if it does not have any dangerous information, that can be done. But then the issue is, if the data becomes very less, then also it doesn't learn anything. So when you try to have a huge tokens, and I think doing this processing is very hard. It's not easy.
Asking this question, there's an overlapping you talking about, and then an issue that was raised like a few years ago about fairness.
Yeah. Yes.
That classifications.
Mhm.
And the conclusion was that the data that we trained was just unfair.
Mhm.
Therefore, based on fair,
Mhm.
feels like the same.
Yeah. So to that defense, it is for classification, we can still hope for, okay, this is a data set, we clean it up. But these models already been trained and millions of dollars have already gone in to train those models. So there is no way, or it is very, very costly to even talking about retraining them. So we have got them. So alignment is our best chance to make them better. Because otherwise, think of it like we need a new OpenAI to retrain them even with the cleaning version of the data. For classification, I think we can still hope for that. But according to me, maybe that is like the optimal solution if we can have like a clean data and then train it. But as per the current state of the art, we already have these trained models. Millions of billions of dollars have gone in to train them. So the best thing is what we can do after, like during the alignment stage. That will really save us. And this is what is being done. There are billions of parameters. We train them to actually behave in a manner we want, or be fair, be unbiased, and all those features. And it ended up being computationally heavy because even if we want to do this alignment, let's just say in our lab, it is very hard to even fine tune like a 7 billion model or Llama model. It requires GPUs access. So it is very hard even to in academic environment. So first, I just discussed like why this is a concern, why doing this fine tuning is a concern. I will give by example, like why even going this fine tuning path is very, very hard, because human values are not just one value. Like you cannot write a rule book saying that, oh, this is what it should satisfy. They changes. A very good example is even the sense of safety while driving, like what you would consider a safe behavior or not. If you take data from India, if you take data from US or Canada, they would be completely different. If somebody is driving very near to me in India, maybe I would say it's fine, it's a safe behavior, but here that is not. So which one you would consider to align the model? So there are lots of things. So there is an inherent diversity even the way people behave. So the humans, there is no one human, gold standard human with which I would align. There are different humans, there are different culture values, different behaviors. So which human should we align our model? That's a big question. So if we say that, okay, let's align them with all of them. They have their own model, right? We can do that. But what it would require, it would require doing that fine tuning for all of those models, right? Which is intractable. Then we would not be able to achieve personalization, and it would require huge computational resources. So diversity is not the only issue. Even the preferences change with time. Think about that, like you have aligned the model. Like a good example is like before COVID word and after COVID words are completely different. People preferences, their dislikings have changed a lot. So imagine you put millions and billions of dollars aligning the model, and then after some time, now the preferences of the human have changed. Now what to do? We can, and then we maybe need to do alignment again and again. But this is the big concern. Like, and doing that parameter based alignment would require lots of computational resources and money. And then again, there are privacy concerns as the users are becoming more and more aware. Because for this kind of alignment, you really need the human preference data set to be with you, then only you can do the alignment. So as the users are becoming more and more aware, they may not be comfortable to share their own preferences with the company, like what they like or dislike for the company to do the alignment. And then last but not the least, most of the models which are really good, they're closed source, closed weight models. For example, no matter how algorithm I can develop good, I can never be able to fine tune ChatGPT because I don't have access to the weights. I can only check it on Llama, which are open source. So a lot of good models are closed weight models. So there is no way we as an academic researchers or in a community, we can even do that. Either we need to train our own model, which is almost impossible, and or we just need use open source, freely available open source models like Llama 2, Llama 3. So these are the issues with fine-tuning models. So what can we do? But we still want to achieve alignment, right? So there comes the big idea of alignment via decoding. So let me go detail into it. So again, we have our LLM. We ask the question. We discuss what is the capital of France. It generates it in a token by token fashion. And the interesting thing is, I didn't define it earlier, but because I wanted to define it at this point, this token by token generation from an LLM is called decoding. It's a decoding procedure. You ask the question and it generates this response. It's called the decoding. Now the question is, can we utilize this decoding process to do the alignment? Because now LLM is trained, we are given the LLM, it is generating the response. Can I change the way it generates the response so that I generate what we want? Because now the task has been defined. We are given the prompt. We want to generate a good answer to it, right? Of course, the quick answer is yes. Now let's go deep mathematically how to define this problem, what is state of the art in this problem, and then what we contributed to this problem. So for that, we need to uh, take a little step back and define it mathematically. We need Markov decision process. There is a state space. And for this example, it is a concatenated sequence of tokens, or you can think of it like set of all possible sentences in English in the world is actually the state space. And then the action space is the next token, which is nothing but essentially the vocabulary. Like given a length, what is the next word or token I would predict? And English vocabulary, you can think is actually my action space. I can pick any word from there. Right? And then a very interesting aspect of this MDP from the standard reinforcement learning is this is called in standard RL the transition model, which actually controls, like for a given state, for a given action, what is the probability of going to next state. And beautifully for this language model task, this becomes the deterministic. So we save a lot on that complexity from standard RL because it is nothing but a concatenation operation. So we are given with a sentence, we generate the next token. The next state is nothing but concatenation. We concatenate and go to the next state. So it is a deterministic model. And then last but not the least, most important thing, the reward function, which is actually responsible for alignment. So we denote our language model by pi. At state t, we input st, where x is our prompt, y strictly less than t is the tokens we have generated so far. When we concatenate, this is also a valid sentence and sequence of, let's just say, English words, and then lies in the state space. And this yt is nothing but the tokens we have generated so far. And then we generate the next token yt from our given language model, given the state. This is how mathematically we denote it. And this pi is called token level decoding policy because it is generating each token by token manner. So we start with t equal to 1. We repeat it for t equal to 2, 3 till end of sentence token. And this is actually mathematically, it is the decoding process. Okay, the sampling from your language model is decoding. And let's see how we can utilize this for alignment. So we have our LLM x, yt is, or to give an example, you can think of that x as that question, what is the capital of France? And yt is, let's just say if t is equal to 2, then y is nothing but Paris. That's the first thing. Okay, and then we concatenate, and then yt is Paris is, that's the next token. So that's what it means. And then the probability of generating the full sentence, we just product the probability t equal to 1 to capital T, and this is denoted as the response distribution, you can say. For a given token level distribution, rho pi is the response level. Like for a given x, the y. So this x is what is the capital of France. Y is Paris is the capital of France. That's what y is here. And we have our pi LLM. And this is the example I just gave. What is the capital? And then this y0, y1 are the tokens, and that is my y. So now how do we know that this given y is good for this x or not? So we need a scoring function, which is called reward model, and which will tell me if you, for example, if somebody would have written there like Washington, D.C. is the capital of France, they should get a 0 reward if I check. And if they written Paris, they should get a 1 reward. That is just like one example. But this reward model would be responsible for alignment. And you can already predict that where I'm going with this is, so I'm given a pi. I want my y to be such that this reward model is maximized. So I will write that mathematical problem for a given model and then change the generation distribution in a manner that I maximize that reward. That's what would be the alignment and decoding. Okay. So I'll get the scalar score. But the important thing is my reward model is at the trajectory level, but my decoding happens at the token level. I need to know which token I should select. So for the trajectory level, this is the alignment problem mathematically, or you can say alignment via fine tuning. What is happening here is this is your reward model, which takes the prompts as an input and your response as output. And this is the Y we generate from our trajectory level distribution. This is the expectation. This is actually just expectation over the prompts. You can forget about it for now. So what this first part is doing, I'm trying to learn rho, which is the distribution, in a manner that it maximizes the reward. So that is where the alignment would happen. But because I start from a pre-trained model, we call it supervised fine-tune model, which was available in the alignment stage, I want to stay close to that because we have already spent in millions and billions of dollars to actually train the pre-trained model. I do not want just for the sake of generating it for reward. I don't want it to forget what it has learned so far. So I'm just fine-tuning. That's why it's called fine-tuning. I'm not like doing big training here. So that KL divergence will keep, that's a negative sign there. It's a maximization. It will keep my model, aligned model, closer to my SFT, but still try to maximize the reward. So this is the alignment problem, mathematical formulation of the alignment problem at the trajectory level, which even ChatGPT used to actually solve it. They formulated it in their paper, and then lots of methods people have been developing to solve this problem. But the decoding is at the token level. We cannot just directly utilize this formulation to do the decoding. So for decoding, we first define a token level reward, which is an interesting redefinition. So which says that when you generate this token, if you have seen the end, if it is end of sentence, you just query your trajectory level reward and give it the reward. Otherwise, it's a zero reward. So it just say like a sparse reward definition for the token level reward. So we have our trajectory pi LLM, which is the token level. We have corresponding trajectory level distribution. In a similar way, we have our reward model. Small r is the trajectory level. Capital R is the token level reward. So this is the token level. This is the trajectory level. How do we do the alignment with these notations? So this is our token level alignment problem for the decoding task. Okay, so there is a jump here. Let me try to explain this. So here what is happening is, you see the earlier problem was for a given prompt at the trajectory level, I'm going to do the alignment. But here, this problem is defined for each T, if you see. So I'm in a state T. I want to select the next token, which I should pick. So if I know the Q star is actually which will solve your Bellman equation in a reinforcement learning task. It gives the value to each token, and it actually, you can see that it has seen the future, and then it knows that which token you predict, and it will lead to high reward in the future. So if you have access to Q star, the first part is just a linear part. Like you have access to Q star, you will select the token which will maximize that, but you want to keep your pi again closer to your pi SFT. So this is an equivalent problem to trajectory level formulation, but with a big difference of, instead of R, I need to use Q star because I'm not checking it at the trajectory level. I need to check for each token. And in the standard mapping to reinforcement learning, you can think you need to know the Q value if you want to take optimal action for a given state. You cannot just take it with respect to the reward. Okay. So this is the optimization problem, where this Q star is our optimal policy evaluation. And the second term is trying to keep my closeness to the SFT model. And this Q star is nothing but, if you have a Q function, you have a policy pi, you try to maximize it, you get your Q star. And the definition of Q pi is nothing but your expected return over your trajectory. Okay, so you have the reward, Z naught is your YT, Zi is you sample from your pi, and I, you start from a given T, and I goes from 0 to till the trajectory goes. And then you take expectation under your policy, you collect the reward, and you define your Q pi. And this problem, you can say the first part is linear, and the second part is trying to make this whole problem as strongly concave, and you can write a closed form expression for this problem, decoding problem. That is also very interesting. So what this closed form expression is, my decoding policy is nothing but my current policy times exp of 1 upon alpha is my tuning parameter, how close I want to be to my pi SFT, and then just that Q star divided by C alpha. So the good thing is, if I know this expression, I know how do I need to change the distribution of my pi SFT to do the sampling. And this is happening at the sampling level, like at the output response generation. There's no parameter of the LLM here. if you see. So that is why it is called parameter free or tuning parameter free, because I'm doing it at a sampling level. Okay. But the challenge here is this term is the bottleneck. Even if we have written a very nice mathematical form and then have a closed form expression, but we don't know Q star. So you can think of it as a chicken egg problem. Like if I already had access to Q star, why do I even need to solve this problem? I could have directly used Q star to do the pi star. Okay. But if you don't use Q star definition, writing this problem becomes very complicated. You cannot write this very nice closed form expression. And the definition of Q star is nothing but we can utilize this trajectory level reward and even your trajectory level model. If you have access to this optimal model, you are in state as C, and this is the first action you take, and then you select your trajectory under your policy. So it's just like I'm in a state, I took an action, and then and after that I follow my policy and calculate the expected value of my reward. That is the value, Q value of that particular action. And then I can calculate it for all. But here again, this is actually long-term reward under optimal trajectory level policy. We have shown that to know Q star, we need to know rho star, but that rho star is also not available in practice. So what is state of the art? That is where we have boiled on. Yes.
Sure. Could you explain again why you're changing the weights of the model? Like what is pi?
Okay. Okay. So that's a good question. So what is pi is? Pi is the probability of selecting a token, and then this pi SFT you can say is what fixed model. Like parameters are fixed, so these are the probabilities are coming from a token, right? Like let's just say there are only 4 tokens, and when I enumerate state as, so this pi SFT will tell me Z1 has some probability, Z2 has some probability, Z3, Z4. So that's the probabilities I know. But I can, if I multiply those probabilities with this value, I get this scalar. I multiply them, I get new probabilities of selecting those tokens. And I can do that without touching the parameter. It is just at the sampling stage. I'm just, because I have this distribution of sampling, I just multiply it and I get a new distribution of sampling. So that I can do without changing the parameters of the model. Because this I can access. Yeah, at all. Yeah.
Because one is, what is this reward function?
This reward function?
Yeah.
So this is given to us. Yeah. Which
for every prompt.
Yes, it should give me the score. What is the good response? Yeah.
The state space is huge.
Yeah. So that's what, like this, they have been offline trained reward models available. For instance, I can give a very quick example. A reward model which will tell me whether the sentence has a positive sentiment or not, for instance. And then we can use any sentiment classifier as my reward model for that. So I will pass my text to it. And if it gives a high score, it is a positive sentiment. Otherwise, it's a negative sentiment. And then I can utilize an LLM to make sure, while maximizing that sentiment classifier reward model, like you generate a sentence which is a positive sentiment for sure, even if that LLM was not generating positive sentiment response before doing this alignment. And there could be different reward model. Like there is a reward model available on Hugging Face which covers the harmfulness of the response or helpfulness of the response. So, and even the alignment is also on an abstract level. It's not just like very specific. It's like I want. Yes.
Okay, so the second question is for the skill star.
Yes.
Like E5, because initially when you define your objective,
Yes.
it's like maximum reward was
Yes.
to get far away from.
Yes.
competition.
Yes.
This one is like just give me the best.
Yeah, so-
I don't care how.
No. This is my alignment problem where I have that KL constraint there.
What is skill star?
Yeah, this is just the definition of Q star. So this Q star eventually I will substitute here only. And then my optimization is still on file. So this pi does not appear anywhere. So you can think of it like this pi will control this token. So this I'm defining just for a given token. So that has not appeared yet. So this is just the definition.
No, what I'm saying is this policy
Mhm.
that you know,
Mhm.
this
Mhm.
for Q star
Mhm.
is there is no constraint.
Yeah, for this optimal one, yes, there is no constraint because optimal just care about whether I maximize the reward or not. And that is where it will become tricky because this rho star is just caring about maximizing the reward. That is true. You're right. But when I'm going to find this pi star by substituting it back, there I will take care of that this pi star is not very far. That is already taken care by this alpha. So that they are connected. Yeah. Thank you. That's a good point. So the whole bottleneck here, you can see that how to get this Q star, or eventually it means that I don't have access to rho star, which is a trajectory level aligned policy. How do I do it, right? So that is where comes like what is popular in the existing literature, and then I will show what was the issue and then what we resolved. That's our contribution. So this is my SFT model, pre-trained model. This is token level, and this is the corresponding trajectory level. And let's just say that is a target, pi star decoding, which is the theoretical. We just saw the solution, right? I want to go from here to here. So I want to do that alignment, right? So to do that alignment, I need to know this Q star, which is actually evaluated at rho star. If I have access to it, I'm done, but I cannot have access to it. So what literature does is they say that you don't have access to rho star, but you do have access to rho pi. That is like a valid, at least a valid distribution. We can generate some responses. So they replace this rho star with this rho pi, get an approximated version of Q, put in the solution we have, and then generate the responses. Okay. Of course, it works better than SFT because they are checking the Q values. And that was state of the art. It is called control decoding. And this is the paper where this formulation was done. But they're not able to go to the target model due to the obvious reasons, because it is not rho star, right? So there is a gap in their performance to the Oracle. So what comes to our observation, or what is our key insight, is actually how to mitigate this gap. So an interesting observation we made is we already have lots of open source model, well-aligned models at the trajectory level with some other rewards which are available online on Hugging Face. That may not be aligned with our reward, what I want, but people have aligned to their reward, what they have. They are available online manner, right? So then we thought is rather than using this language model, we will use that language model aligned with some other reward, which we have information of, and then we do some sort of transfer from that reward to the target reward. And then if it works better or not, that's as simple as that, right? And that's what we did. We took a baseline model, which is not aligned with target for sure, which is aligned with some other reward. And then we actually use that to replace rho star, not the rho pi. That's the basic idea. So we are doing transfer from there to decoding. So of course, because our is also an approximation, we don't have access to rho star, but our approximation is definitely better than state of the art. So in other words, the basic contribution we do is we do a better Q function estimate, as simple as that. And we have a better estimate of Q, of course, we are going to perform better than state of the art, and that's what we achieve. We are not able to touch the Oracle because we cannot have access to rho star, and I think theoretically it should be impossible to do that, but we can go as close as possible. But this idea works really well, and that is why we call it transfer decoding rather than control decoding, right? And the mathematical intuition is what we exploit is that is actually the trajectory level closed form expression for the parameter solution. Like if you have a reward model, you have a rho SFT, that is the closed form for that. And this is what we call TQ star rather than calling it Q star, because we are using rho small r rather than using rho star. And what we did is that is the definition of Q function. We multiply and divide by rho BL, that the baseline we introduce, which we have access to. So we get this ratio. So now the thing is, if I know this ratio, I should be able to do the transfer from any baseline policy to any target policy. And that is where the trick comes in. So we utilize that expression, write my baseline reward in this form. And similarly, I can write my reward in the same form between R and SFT and BL and SFT. And with just some simple algebra, you can obtain this closed form expression, which is nothing but rho R in terms of rho BL reward difference between the ratio of their normalizing constant. For instance, if you ignore the normalizing constant, you can see that I can bring this BL here. So I get this ratio directly proportional to the reward difference. So I can use this expression directly there and then estimate my TQ star, right? And it is very interesting and intuitive because it is doing the adjustments for me. So I have a baseline model which is aligned with RBL, and I want it to align with R. So what it ended up doing is it ended up changing the probability proportional to their difference. So if this difference is 0, it means I already have a model which is aligned with the target reward and I will directly use it. But if it's a little bit different, you will try to force it into the direction of going towards the target. So, and that's what we did. This is our proposed algorithm. We start with initialization. This is the base model prompts. We generate the token, and then we actually propose two algorithms. One is direct transfer and the other is indirect transfer. Direct transfer means when I have baseline directly for the reward model, I'm going to do the alignment. And the indirect transfer is where I do this correction when there is a difference between the reward. And once I have access to TQ star, this step is easy. Instead of Q star, I will use TQ star to estimate my decoding policy. Once I have my pi star, now I will sample my YT. So here we have not touched the parameter of the LLM. They are fixed. We are just changing the sampling probabilities. And then we do the next thing. And this is the algorithm. And we have shown even the suboptimality gap of our proposed algorithm, which is clearly you can see the first term is being controlled by parameter beta, and it's actually a constant. Rho star is optimal, rho FFT, I don't have any control to. The second term is alpha, which we introduced. And interestingly, it is negative. And we can control this gap by controlling that alpha higher and lower. So one remaining open question, which we still are figuring out, is what is the exact mathematical rate of that h of alpha with respect to alpha? So it was not coming out very nicely, but one thing is for sure that the h of alpha x expression was always positive. So it appears in a negative, which means I can make this gap very small by controlling alpha. So because that is not the only goal, as you raised, like, okay, how far I will be from my base model. So we also provide an upper bound, which is like, as you can see, it is very intuitive, controlled by the parameters by beta and alpha. So if I have my alpha infinity, so I will just focus on the second part. I can make it small, as I will not move. But if alpha is small, I can give it a room to improve. So these are the two. We have theoretical results in the paper. So experiment-wise, so this is our proposed idea. So we use Mistral 7B for the base model. And for reward model, we use a reward model, which will check the text for being relevant, helpful, and ethical responsive. And then for the baseline model, we use Zephyr 7 billion. And this we show, like, these are the existing state-of-the-art approaches. The average reward, the proposed algorithm is able to achieve better response. And then we also show in terms of KL divergence, because it could be really problematic if our reward advantage is coming by going away from KL, because that is also possible. So it becomes extremely important in alignment papers. Like, we show both, like how good or bad we are doing in terms of KL, and now how good or bad we are doing in terms of reward. So that was just one configuration I shown. So we have done 6 different evaluations along selecting 6 different language models. And the interesting thing is we did not train any of them. They are all freely available online. We just use them, did the decoding, and then show the performances. So this is without parameter tuning or anything. Okay. And then also another angle is, like, we even showing reward maximization is not sufficient, because reward model might be incorrect, or we don't know what is the optimal reward model. So another standard in literature is we show GPT-4 win rate. Like, whatever we respond, we'll ask GPT-4, like, okay, what do you think about our response? And we show our comparison with GPT-4 win rate, and it was able to win in a lot of evaluations. And another thing, we show an aberration showing that if my reward models are very different, like the one I'm using and the target one, as you can see, as their gap increases, because we are correcting for the difference, we are able to maintain the performance. While existing state-of-the-art approaches, if the reward difference is very big, they just drops the performance, because there is no correction happening using the reward difference that we proposed. Okay, so this is definitely a cherry-picked example, but because I have shown statistical results, so I just wanted to show one example where it really shows that it is working. It is not just generating some garbage and then trying to maximize the reward or hacking the reward. As you can see, the prompt is, how can I convert the decimal number 31 to binary format using JavaScript code? Can you provide the code for this conversation? So the first is, like, it is not even the correct answer. The second one is trying to do it, but if you run, it doesn't work. With our method, this is the response. And if you run it in JavaScript, it will work. So that's the response generation. So in conclusion, we propose a novel decoding strategy called transfer decoding. We provided theoretical and empirical results. So as a future, we believe this decoding has huge impact, and then huge scope in terms of developing personalized product recommendations with LLM. And then inference time alignment can also help us induce various behaviors without changing the parameters. So now just imagine that you just need to give me a new reward model. Like, I want your LLM to behave in this reward. I'll just use the same LLM, and I can align it to different reward model. And we can also solve the diversity problem and even the privacy problem, because what one can do is, there's a community, they can just share their preferences within their own community with someone who is training the reward model. And then I can just show that reward model to an LLM, asking that, oh, generate responses which are maximizing that reward model without even sharing the preferences of those people directly with the government. So yeah, thank you so much. I think, yeah, I'm happy to answer any questions. Thank you.
Okay. Questions?
Yes, thank you.
Can you maybe give an example of a pipeline? So somebody asks for something and the factual answer comes out, even though hallucination might have been produced somewhere along the line,
Mm.
or someone has to make a bomb and somehow the decoding process filters that out before. I'm just not sure how you get from point A to point B or F or whatever it is.
Okay, so that's so let me try to answer. I don't have the perfect answer to that, but let me try to see. So when I ask an LLM, for example, let us take an example of how to make a bomb, and then when it takes that in, and then it passed through the parameters. So the only thing I have access to, because I do not know what is happening inside, is it give me top K tokens. Like, oh, these are the top K tokens, and for example, it would say sure, I can something. These are like 4 possible tokens with which it can generate the response. And if it is a good LLM, it will have the probability of selecting I higher as compared to selecting short. Because if it selects with I, it can write a sentence that I cannot answer. But if it starts with sure, the next probability of selecting the token is sure. Here is the answer. So I don't want that. So looking at those token probabilities, I can still guess what it is going to write. But before that, what is happening, that I don't know. We just have access to the output token probabilities. And that is where the safety features comes in. I can see 2-3 tokens it generates, like sure, here is how to make it. I can stop there. I can check whether now it is like if I check it with respect to a safety reward, it will give me a very low reward because an unsafe response. So I can stop and say that, oh, I'm not going to generate an answer to it. So if it generates like I cannot, it's a safe response, it can generate. There are lots of things people are proposing. You can also put those filters at the input also. If you ask how to make a bomb, it will pass through a prompt filter before going into the big LLM, because it will to save on the compute, because there are billions of parameters. So if it is like an unsafe question, how to make a bomb, how to haywire a car, or like how to rob a bank, it will just have a standard response saying that, oh, I'm not going to write to it. So that is the place from where I understand it. But of course, there must be happening something within the neural network saying that, oh, due to this neuron, this led the response. But yeah, that part I am not very sure.
Where does Mistral or Zephyr, one of these open source well-aligned models, come into play?
So we are using for our experiments.
I didn't misunderstand what you're saying. I thought that they were using that you were using them as some kind of filtering mechanism for the tokens that come out. That if not, then what are these open source well-aligned models? How are they serving your project?
Yeah. So they are serving because the thing is, let's just say I take this open source LLM, let's just say Zephyr 7 billion. I'm giving an example to explain that is not in our paper. But if I ask it how to make a bomb, I don't do anything what we propose. It will generate, here is the way how to make a bomb. There is a detailed explanation. But when we do this decoding, what we propose, like the way you generate an answer from the same model, it will give an answer. I cannot generate a response. It is an unsafe query. That is where, so I will control the generation part, like how it is generating the answer. That is where it will play the role.
Okay, thanks.
Thank you.